Good morning, COS 101 students. Hope everybody's doing well. Keeping with what I've been doing for the last last week or so, I'm going to go over a PowerPoint slide that highlights some of the things you'll need to know for the test. So today's class, it will be brief, should be less than 10 minutes long, highlights the communication errors PowerPoint slide. So I'm going to share the PowerPoint with you right now. So, and we're going to go over it a little bit. So computers communicate with each other all the time. That means, every time you get on the internet, you're communicating with a server. Could be your bank, could be internet, it could be a game server, whatever you're doing. Everything you're doing on the internet is communicating with a server. So some of that communication isn't critical. If a pixel changes color or you get a little bit of improper communication, it's okay. But the problems occur when there is critical communication. Critical communication could be using Venmo to transfer money to your friend for lunch. If the amount of money you transfer is wrong, that would obviously be very critical. So how does one computer know when the communication to another computer is incorrect or has a problem? Well, this is a big issue in the field of computer science called data integrity. And what I'm going to sort of introduce you to today is just a very brief, simple system that is clearly not in use anymore because it's too simple. But it was the very first system. And if you're interested in this field, this is the field of part of computer science called communication software. So, and it's embedded in a lot of the software that people use. So this very simple system basically can detect a single bit from a 8-bit pattern, whether it has been communicated correctly or not. So this is a single bit detection system, and it is known as a parity bit. So this is what's on the test. You need to know what a parity bit is. So the system works in the following way, right? Every single 8 bits, which is a single character code or a single pixel code, is written using a 9th bit. So another bit is added to every 8 bits. So instead of a byte having 8 bits, really a byte has sort of this extra bit, the 9th bit for every 8 bits. And the system I'm going to talk to you about is called even parity. And everything I say about even parity could also be said for odd parity. But so even parity is the following. It's essentially, you look at the 8 bits that are in your real data. So the real data consists of 8 bits. And if it has an even number of ones already, in other words, there are 2 ones in that 8-bit pattern, or 4 ones in that 8-bit pattern, or 6 ones in that 8-bit pattern, or even 8 ones in that 8-bit pattern, then that 9th bit, called the parity bit, is set to a 0. On the other hand, if the 8-bit in the real data has an odd number of ones, there's 1 1, or 3 ones, or 5 ones, or 7 ones. Those are odd numbers. Then the parity bit would be set to 1. Well, in either case, what does this mean? This means that, and this is important, this means that all 9 bits are now set. Whoops, let me go back. This means that the 9 bits always have an even number of ones, because if it already has an even number of ones and the parity bit is 0, and it still has an even number of ones. If it has an odd number of ones, by setting the parity bit to a 1, you've just increased the number of ones by 1, making it now an even number of 1. So in either case now, the 9 bits, the 8 real bits plus the 1 parity bit, has an even number of ones. That's known as even parity. Same kind of thing could be said about odd parity. Well, the result meaning that if a single bit flips along the way, then the 9 bits no longer has an even number ones. Now it has an odd number ones. So as an example, if you look at this, these are in bold is the 9th parity bit. So in this particular example, you have 1, 2, 3, 4, 5 ones in the real data. And then the parity bit, that 9th bit on the left-hand side, is set to 1 here. So now those 9 bits now contain 6 ones. Second example underneath here, we have the real data has 4 ones. So therefore, the parity bit is set to 0. That way, in both of these two cases, the 9 bits that are getting transmitted have an even number of ones. And if for some reason along the way a bit is corrupted, any one bit is corrupted, then the receiving computer would see it as having an odd number of ones, and say the receiving computer would say something's wrong here because it has the wrong parity. That particular 9-bit pattern has the wrong parity. If nothing's wrong, if the transmission went okay, then it sees 8 bits. Now, the only time you can get into trouble here is if 2 bits flip, or 3 bits flip, or actually 3 bits flip would be incorrect data, while the computer would see it as incorrect. But 4 bits flip, and then you have a problem. So then it becomes a question of, well, what's the likelihood of those particular events happening? And that's why there are more elaborate systems. So what you need to know as far as test number 3 goes is a parity bit. What is a parity bit? All right, so there is some more things on this particular slide that you don't need to know, but there are more elaborate systems which use what one's called a Hamming code, where you add more extra bits, 3 bits, a 3-bit addition to every 8 bits, so now you have 11 bits, means that the system would be able to detect 2-bit flips and self-correct a single-bit flip, and so on. And there are more elaborate systems. Basically, the more bits you add, the more detection you can perform. So the downside here for these more elaborate systems is that it's slower because you're adding a whole lot more bits. All right, so really what I mainly want you to know is about this kind of a question that I won't ask you to write a paragraph. It'll be a multiple choice test, but the additional of a single bit to every byte enables the communication software to detect certain levels of bad data, and that is known as a parity bit system. That's what you need to know for the test. All right. Thank you, one and all. I will return again tomorrow, or actually probably Thursday, with some more information on the next slide that I wanted to go over. And hope you all have a good day.